In this video, we're going to learn how to count the number of proper colonies by using the inclusion-exclusion formula. The inclusion-exclusion formula says that given lowercase n subsets a sub 1 through a sub n in a universal set with a capital letter N element, if S sub k denotes the sum of the sizes of all k tuple intersections of the a sub i's, then to count the number of elements in the complement of the union of a sub 1 through a sub n, we have to include the universal set, exclude one set, include two sets, exclude the three sets, and keep going. Then we can have this equality. So how to use the inclusion-exclusion formula to count the number of proper colonies? More precisely, given a positive integer k and a graph G, how many proper k colonies of graph G are there? First, what is a proper k colony? A proper k colony of a graph G is a labeling from the vertex set of graph G to a set S with size k, such that adjacent vertices have different labels. So this is a hint. Adjacent vertices have different labels. So if you want to use the inclusion-exclusion formula, think about the left side. We have to think about the complement of a sub I, right? So for each edge, we probably want to have the same label on the end vertices of each edge. So we can set up a sub I in that way to use the inclusion-exclusion formula. Suppose that the edge set of graph G consists of the m elements e sub 1 through e sub n. For each I between 1 and m, we can let a sub I be the set of all k colonies of graph G such that the end vertices of the edge e sub I have the same labels. Then the number of proper k colonies of graph G is exactly same on the left side of the inclusion-exclusion formula. So by using the inclusion-exclusion formula to compute the right-hand side of the inclusion-exclusion formula, first we have to compute the capital letter N, which is the number of all k colonies, not necessarily proper. This means that if there are n vertices, then each vertex has k options, and there are n vertices, so we have k to the n options. And to compute S sub 1, okay, so for each I between 1 and n, okay, we want to compute the size of a sub I. Okay. A sub I is corresponding to the edge E sub I, and assume that the E sub I have two end vertices, say U and V. So U and V must have the same label. Okay, so E sub I in here and U and V. So those two vertices have the same label, which means that for those two vertices, we have k options because we have a k colored. Okay, and in the remaining vertices, n minus 2 vertices, okay, and each vertex has a k options. So in total, this is a k to the n minus 2, and this is a k. So, sorry, this is a k to the n minus 1. Okay, because there are m edges. Okay, so to compute S sub 1, okay, we need to multiply m choose 1. Okay, so S sub 1 is equal to m choose 1 times k to the n minus 1. Okay, more generally, to compute S sub j, what do we have to do? Okay, assume that j is equal to 2 and n is equal to 6. Well, so to compute the S sub 2, okay, maybe you can think about two edges, say E sub 1 and E sub 2. So you have to think about the set A sub 1 and A sub 2 corresponding to the edges E sub 1 and E sub 2. So to compute the S sub 2, you should think about the intersection of A sub 1 and A sub 2. What does this mean? This means that the end vertices of the edge E sub 1 have the same labels, and vertices of the edge E sub 2 also must have the same label. Okay. So actually there are two cases. Those two edges are not instant. Okay, so because there are n is equal to 6, so we have this situation. Another case is E sub 1 and the E sub 2. Okay, they are instant cases. So this is E sub 1 and E sub 2, sorry. Okay, and the remaining verbs is in here. So for this case, okay, because those two end vertices must have the same label. So for those two vertices have the K options. And similarly, those two vertices also have K options. And in the remaining vertices, each vertex has a K option in here. So in total, K to the 4. Okay. And for this case, E sub 1 and the vertices of E sub 1 must have the same label, and the end vertices E sub 2 also must have the same label. This means that those three vertices must have the same label. So for those three vertices, we have K options. And in the remaining vertices, each vertex has actually K options in here. Right, so this is also K to the 4. How did we get actually K to the 4? We actually count the number of components in the spanning subgraph induced by the edges, actually. And in this case, E sub 1 and E sub 2, those two edges. Actually, you can see there are 4 components in here. This one, and those two. And here also there are 4 components. This one and those 3 things. So for j is equal to 3 or even 4, okay, more generally, okay, we actually just want to think about the number of all K colorings of the spanning subgraph induced by just the J edges. Okay. Then actually the number of proper colorings there actually K to the number of components in the spanning subgraph there. Okay. So S of J, well, because we should think about the all J elements edge sets. Okay. So that's why we have in here. Okay, and then we should think about the number of components in the spanning subgraph induced by the J element edge set S. Okay, so actually to determine the left side of the inclusion-exclusion formula, actually, we don't want to think about the certain number of edges actually, okay, because we just want to get the summation of all edge sets. But to use the inclusion-exclusion formula, okay, so depending on the size of S, we have to think about this factor. Okay. Thanks for watching.